Alright, so last time we started talking about light and we did a lot of physics. Why are we doing all this physics? That's a good question. So I don't want you to forget the big picture. What we said was that different elements emit different light. Think about fireworks. And if we analyze the light emitted by different elements, we can learn about their structure. What does an atom looks like? And that's what we're trying to get to. Analyze the light in order to understand what their structure looks like. What does an atom looks like? And we studied the light. We said light behaves like a wave, like a particle, quantized energy. And then scientists put everything together, came up with a Bohr model. And then we also went over every time you excite a hydrogen atom, you see 4 lines. Why is that? Rydberg came up with an equation to fit that, and we have all this beautiful Bohr model that here's a nucleus, you have energy level around it, the spacing matters, and then electrons have a quantized energy. So if you excite an electron, you have to have enough to go to the next level, otherwise it would come back down. This was great, but there was a problem. This model is too simple. Why is it too simple? Because it explained hydrogen atom beautifully. We could explain everything about a hydrogen atom, why we see 4 lines. But we couldn't explain any other elements. And because hydrogen atom has only 1 electron. If you have 1 electron, it's beautiful, everything can be explained. But if you add another electron in there, then the model wasn't working. So it was too simple. It's kind of sad. But on the bright side, they've learned so much from this model. So the learning point was they learned about quantized energy. And that was really key. Okay, that was really key because now we know that electron need to have enough energy to make it to the next level. You can't have half, you would come back. So you need discrete amount of energy to make it to the next level, and then the spacing between the energy level matters. So this was really good to learn. Also, the other thing that we learned is that energy is involved. Energy is involved between the energy level, between the levels. Okay, so we know we have all this energy level, we learn about the spacing and all that, and also we know that energy is involved between the levels. But this was too simple. This was only explaining the hydrogen atom and nothing else. But, we learned something about it. The quantized energy was really big. Now, more scientists had to come up with different ways to understand this more. The next scientist was de Broglie. We're going to talk about a few more scientists who came to explain this. Now, if you remember, last time what we said radiant energy, which is just a fancy way of saying light, right? Radiant energy behaves like a wave and behaves like a particle, right? We went that and we went over the equations for that. Now, de Broglie said, here is a crazy idea. How about electrons? What if electrons also have wavelengths and how about electron also have wave and particle characteristic? That was a crazy idea at the time. We said light behaves like a wave and particle. He said, well, how about electron behaves the same way? And what he proposed this equation. Lambda is equal H over mv. Okay? And I'm going to go over how he came up with this equation, because sometimes it really helps to know how people came up with this equation. It makes you understand it a little bit better. Now, before I go over that, let's go over this. So wavelengths, you know what wavelengths is. That's a wavelengths, right? Let's go to H. What is H? You also know what H is. Is Planck constant, right? We had that from last lecture. Now, what is M? M is mass, is in kilograms. What is V? V is velocity. What is mass times velocity? Mass velocity, what is that? People who love physics, that is momentum. That is momentum. Okay, that is momentum. All right. Now, anything with mass and velocity also has a wave characteristic. And particle, they have mass and velocity. So we are kind of, the newer all the little pieces, we just put it together. All right, so we have a mass and velocity because particle has a mass and velocity, and then we have a Planck constant in there, and because we said that electrons also behave like a wave. Now I want to tell you how he came up with this equation, but before I do that, what I do want you to know, I want you to put another box around this. This would be our last equation, okay? And now let's go over how he came up with this. You don't really have to know this for this class, but like I said, it really helps to show you how he came up with this. What is Einstein? Famous equation, EMC squared, right? And that is for electron behaving like a particle, right? Particle has a mass and velocity, okay? But we also said that electrons are going to behave like a wave. So hc over lambda, because we also said they are going to behave like a wave. Okay. So can I add these two together? Sure. Can I equal them to each other? Sure. Because we said electrons can act like a particle and it could act like a wave. So I can equal these two together. If I equal these two together, I get mc squared equals hc over lambda. So this is my wave. Oh my goodness, why did I do that? This is my wave, this is my particle. Okay, so particle and wave have the same traits. Now here is a problem. Particle cannot travel at the speed of light. Do you agree? Particles, they can't travel at the speed of light. Because particle cannot travel at the speed of light, what we are going to do, we're going to substitute speed of light for velocity. We're going to sub speed of light for velocity. If you do that, then I would be mv squared equal hv over lambda. So far so good. Okay. Now all I'm going to do, I'm going to solve for lambda alone. I'm going to isolate lambda. If I do that, it would be lambda equal hv over mv squared. We're almost there. Now, I'm going to cancel out whatever I could cancel out. I could cancel out the v. Why do I keep doing that? And the 2 goes over there. So then that would equal h over mv. And voila, that is our equation. Was lambda equals Planck constant over mv. So far so good. Again, you don't have to know this page, but sometimes it helps to see how he came up with this crazy equation. Alright, so that was good. He broadly said electrons behave like a wave and like a particle, just like a light. Now, next scientist was Heisenberg. Heisenberg came up with an uncertainty principle. Now, what is that? If you had physics, you probably remember that. Let's say I have a ball. Here's what it says. Classical physics, it says you can calculate the position and the speed of the ball with accuracy. But the modern physics says you cannot know the momentum and the position at the same time. So what it's saying is you cannot know the position and the momentum. You cannot know it at the same time. You can only know one thing at a time. Does this make sense? It is actually one of the few things that does make sense. Okay, I have a good example. I don't know baseball, so kind of go with my example. Let's say I have a bat, and you're going to pitch the ball to me, and I'm going to hit the ball with my baseball bat. By the time you hear me hit the ball, where is the ball? Is it at my bat? No. By the time you hear the bam, my ball is somewhere else. So I cannot know the momentum and the position at the same time. It's the same thing. By the time you see the electrons, there might be somewhere else. Remember how sometimes they say, you read it on news, they say like some of the stars that you see, by the time we see them, they don't even exist anymore? It's the same thing. You cannot know the momentum and the position at the same time. By the time I see the electron, they probably are somewhere else. Okay? Alright. So then, we are going to have a revised model. So the Bohr model was too simple. We are going to have a revised model. And our revised model, what's going to do is going to take everything into consideration and describe the position of an electron as a probability. So what does that mean? What that means is the location of electron. The location of electron is just a probability. Why is that? Because we cannot know the momentum and the position at the same time. By the time you see the electron, they're probably somewhere else, but we can say probably this is the position of the electron. Okay? So it's a probability. This is really key. It's just a probability. All right. Last scientist, Schrödinger. Yes, the guy with a cat. He put everything together. He said, we said electron behave like a wave and behave like a particle. And then he did a lot of math. I'm just going to write down math. And he came up with a light function. And what he came up with is probability of finding electron. Don't worry about this, it's just like a function. Now, this is a wave function. So now, they've considered everything, the probability of finding electron being wave and particle, and what they came up with is quantum mechanics. Quantum mechanics is such a complex topic, but I don't want you to ever get lost. If you take more classes in quantum mechanics, get lost in the math. Because I don't like math, I always look at this as a conceptual way. Don't get lost in the math. I'm not even going to go into math. In this class, we're not going to do it. If you take a physics class, you're going to go over all the nice, complicated math. Here's what I want you to know about quantum mechanics. What does quantum mechanics tell you? I need you to remember this. That quantum mechanics tells you where are you most likely going to find electron. Where are you most likely going to find electron? That's what the quantum mechanics tell you. I'm going to write this down because I want you to not forget the big picture. Where are you most likely? Why is it most likely? Because we can never be sure. Where are you most likely going to find electrons? Okay? All right. So, finally, we're almost done with this lecture. I want you to remember that Bohr model was too simple. And the reason that the Bohr model was so simple, because the only thing that it had N. It had the energy level, right? We have the nucleus and we had the energy level. The electron could go higher. They could excite to the higher energy level and they could come back down. And we said this was too simple. But it gave us the energy level. Now, our new complicated model, quantum mechanics. What does that gives us? That gives us N, L, M sub L, and M sub S. And we will go over what those are. But here's what I want you to remember. That the Bohr model, which you usually go over in high school, that was too simple. But it did give us quantized energy, and we learned about the spacing and all that, and we learned about the hydrogen atom, but it didn't work for anything but the hydrogen atom. It gave us the energy level. That was too simple. Quantum mechanics takes us to the next level. It's going to get us the N, the energy level, also L, M sub L, and M sub S. Now, what are these things? Even though I haven't taught you what they are, I always want you to understand the big picture. Here's the way to look at this. If you had to find someone, how would you find someone? Do not tell me you go to Facebook and find them. Don't tell me that. Old school way, back in the days, how would you find someone? Yeah, right now social media, stalking someone is probably the best way to find them. But back in the days when there was no social media, that wasn't a long time ago, to find someone, you would use yellow pages. You probably have no idea what that is. Ask your parents. Yellow pages, great thing. Now, to find someone, you would find them based on their address, not based on their social media. Now, how would you find someone based on an address? When you have someone's address, is there the house number, the street name, and their town, their city, right? What's your street name? What town you're in? What's your house number? That is the address to find a person. Now, N, M sub L, and M sub S, the way I look at this is an address for electron. Look at it this way. This is an address for electron. What does that mean? It's going to tell me the location of an electron, except the location of an electron is a probability. The location of electron is a probability. But it gives me the address for electron, right? The location of the electron is a probability. So just think about it. If you want to find someone, you find them based on their address, their house number, their street name, their city, and their town, and their state. This is the same thing. These four information is the address for electron. I'm going to be able to find the electron, except it's always a probability because we can never be 100% sure. So far, so good. Okay, beautiful. Really, really nice job. Now, I want to do a practice problem, okay? And then we're going to pick this up and go over what are these address for electron. Now, here is, I was going to give it as a take-home problem. But you know what? I'm actually going to go over it with you right now. Here is a practice problem. Which emission has the lowest wavelengths? Do me a favor. Pause me. Please pause me. Go over this, do this problem, and then unpause me. Okay, now that you unpause me, let's go over this. Which emission has the lowest wavelengths? The first thing that should stand out to you is that, emission. Emission is we go from the higher energy level to the lower energy level. So which one can I automatically quickly cross out? I can cross out A because A is absorption. So I'm now between B and C. Okay? So which emission has the lowest energy? You could actually do the math, but that would take a long time. But don't do that. You can do this in a shortcut. Remember the equation that relates energy and wavelengths is over here? Okay. I'm asking for the lowest wavelengths. The lowest wavelengths would have what? The highest energy, right? Because they're going to be inversely proportional. Lowest energy would have lowest wavelengths would have the highest energy, because what I'm looking for lowest wavelengths, and the lowest wavelengths would have the highest energy. Now, which one have a higher energy, B or C? Think about it this way. if I do a small jump versus if I do a big jump, which one would I need to use more energy? Small jump or big jump? Probably the big jump, right? The bigger the jump, the more energy you have to use. The bigger the jump, the more energy you have to use. It's exactly the same thing. So B and C, which one has a higher energy? C has the higher energy. C has a higher energy because it's a bigger jump. So higher the jump would be the higher the energy. So C would have a higher energy. And higher energy means what? Means lower wavelengths. So the answer would be C. So far so good. Hopefully you guys got that. Again, A is not absorption. You knew that. Between the two emission, the one that has the longer gap, the higher jump, is going to be higher energy. Look at it this way. If I do a small tiny jump versus a big jump, of course the big jump, it has more energy. I have to use more energy. So this has a higher energy, which means lower wavelengths. Yeah? Okay, beautiful. Really, really, really nice job. Now, what I want you to remember from today is that quantum mechanics tells you where are you most likely, and most likely is the key, going to find the electrons. And Bohr model was too simple. It only had an energy level. Quantum mechanics adds so many more levels to it. And the way to look at it when things get so crazy, remember, it's kind of like an address for an electron. Where can you find it? Except it's always a probability. All right, very nice job. I will see you guys next time.